let me summarize again what we did. We talked about the differential pair. When you think about the differential pair, right, at least in this class or any properly designed differential pair, you will think that it is symmetric. It's absolutely symmetric from left to right for it to work well. So in this case, even I say M1, M2, basically we mean M1 and M2 are identical, right? So you can make this assumption or you can confirm, right? RD needs to be identical. On the left, it's just like a common source amplifier, except that we actually have a tail current here to bias to both branches, right? And this differential pair is like that. Just like any circuit we have learned before, you need to bias it at the right operating regime, right? Which regime do we prefer? Saturation, yeah. So we need to bias it at saturation. So definitely I cannot apply negative voltage to here unless this is negative, but this is ground, so this cannot be negative, right? So I need to apply a certain gate bias. In this example, I say I apply 2 volts to the gate, just an arbitrary number, makeup number, right? The VDD, I don't know, can be 5 volts if you want, right? Just an example, maybe 5 volts, right? So when I bias this, then of course they are symmetric. Because they are symmetric, the current going through the left and the right branches have to be the same. And they need to add up to ISS. And because of this, the left current, which is ID1, needs to be ISS divided by 2. The right one needs to be ISS divided by 2 also. So they add up to ISS. Is that okay? So this is the backdrop of the whole game. You need to see this. And then after that, we will apply a small signal to it. Just like what we did for common source amplifier. If we were just common source, we bias at 2 volts, and then we apply the small signal for amplification, right? So when the left goes up and the right goes down, I forgot to say that, and because it's a differential amplifier, we're going to apply a signal which is differential again, right? One of them will go up, the other will go down. They always go in the opposite direction by the same amount, about the common mode level, right? We talked about differential signal last time. Maybe we should relate this to it in this particular case. You have a T, and we bias it at 2 volts, which is the common mode, right? We bias both of them at 2 volts. And then we have 2 signals. One is going up, and the other is going down by the same amount, right? And that is what we care about. Is this okay? We measure the difference. Now, if the left one goes up, then the right one needs to go down, like we say here. And then when I increase the left voltage, intuitively, you will think that the current is going to increase on the left, right? Because the VG increased, the VD tends to increase. Although we don't know what happened to Vx, but looks like that is correct. It's not inertia, right? So, and the other side, the voltage goes down. We try to turn off this transistor closer to turn off. So the current is going to go down, right? So on the left, we increase by 10 microampere, and on the right, it reduced by 10 microampere. The total current is still the same, right? I take something away from the left, I add something to the left and take something away from the right, right? When you add them together, you still equal to ISS, right? And because of this, I have larger current on the left, so I have more potential drop. So Vx is going to reduce and Vy is going to increase, right? So in this numerical example, we say the gain is equal to the change of output. And the output, again, is not the one of them. It is the difference of them. We are looking at the differential output. So the difference becomes 3.9 volts minus 4.1 volts divided by the change of input, 2.01 volts minus negative 1.99 volts, right? If you already see the DC bias, you just want to work on the AC direction, it is the same. It is this, you see, this is negative 0.1 volt plus 0.1 volt, right? So this is still negative 0.2 volt on top. And the bottom is 0.01 volt minus negative 0.01 volts, which give you 20 millivolts. And the gain is negative 10. Is this okay? Think about it. Any questions? If no, then let's move forward, right? So now, we start really going into the detail to study the property of a differential amplifier. The first thing we want to learn is the common mode response. Again, what is common mode? Common mode means your left and right is a differential pair. The signal we want is going to be differential. But now I want to see what if I don't apply a differential input. I just apply a common mode input. I make them go up and down at the same time. It's basically just like in this case, I change the VCM. Instead of 2 volt, it becomes 2.01 volt, 1.99 volt, keep swinging up and down. Common mode signal. Is it okay? Common mode, okay? So what happens if I have a common mode input? What is V out? Now, first of all, by definition, we are talking about the differential pair I gave you on the left. V out is what? Vy minus Vx, right? Again, I try to look at the difference of them, okay? So the common mode gain, by definition, in this case, common mode gain is Vy minus Vx, which is the output, because we only care about the differential output. But now the input is some common mode input, right? Basically, it's saying that if I increase the input common mode by 0.1 volt, what will be the change of the difference of the output? Because this is what I'm sensing. Make sense? Any questions about the problem, the statement? Okay, if no, then let's think about this. If VG1 equals to VG2, right? Because now it is common mode, right? I do change the gate voltage. But is this circuit still symmetric? If I make both VG goes up and down, is it still absolutely symmetric, this circuit? Or on other hand, if you were an electron here or here, do you feel the same electrical potential? Do you feel the same environment? If both of them have the same gate voltage? Yes, right? So they are still symmetric, regardless of what value you have. So in that case, should they have the same current, left and right? Yes. Yes, right? Because you're going up and down, right? So ID1 must be equal to ID2. And if that is the case, what should be ID1 and ID2? ISS divided by 2. Now, then I want to ask you, what is Vx and Vy? I claim that they are the same by using KVL.
VDD minus RD times I flipped by.
Oh, very good. VDD minus RD times ISS by 2, right? And this does not change, right? So because of this, ACM equals to 0. So basically it's saying that, well, even you change the common mode input, the differential output does not change. I still feel them, they are the same. Okay? Now, this go back to at the beginning, I asked you how to solve the noise problem, right? We have and then we become a 2 common source amplifier. And then I say, can we, but then there's a problem if we apply the positive input, the input instead of differential input to the two common source, we get no gain. How can we solve that? One of you say that, let's only apply the input to the left branch, but the right one, we don't do that, right? And that one still can solve the noise coming from the VDD, but you cannot solve the noise coming from common mode. So this common mode basically is just a noise. Okay? So you see that with this differential amplifier, even I have noise due to common mode, because we always need to bias our circuit at common mode, and I want to amplify my small signal, differential signal. But if I have noise from the common mode, this one can suppress it. Because even you have a fluctuating, because I only care about this differential output, I don't have any common mode gain. Is this okay? Now, some of you might feel uncomfortable because when you answer this question, everything looks correct. Yeah, there will be no gain, but why increasing the gate voltage is not changing the current? Why is that? That is right. No more current can be drawn because you have an ideal ISS. But how this transistor responds to fulfill this criteria? Isn't that IDE proportional to VGS minus VT squared? Now VG increase. Isn't that my ID should increase?
No, but your reach also increase.
So the only possibility is because Vs also increases, right? So very good what you're saying. This one goes up, but no one say that this one need to stay a constant bias. And luckily, because this is an ideal current source, even you change the Vs, I still have the same ISS. And later you will see that when it's not ideal, you will get into some problem with this one, right? Yeah, question?
How would Vs increase? It's connected to ground.
Is it connected to ground?
It's connected to a current source.
It's connected to a device. Current source is a device, right?
Yeah.
So is this grounded?
No.
No, right? So it can be any voltage that allow ISS to operate. So you will find a solution so that it fulfill all the KCL and KVL. Yeah, very good. So this one can change. It's not connected to ground. Right? So this solve our problem, our intuition problem. Yes, yeah, VG increase, no problem. Vs can come up so that I still fulfill the sum of the current to be ISS. Okay? Yeah.
In an ideal scenario, wouldn't the voltage before and after the current source be the same?
Ideal scenarios are before and after. You see this one?
Yeah.
Current source doesn't care about the voltage across it, right? It only care that you deliver a constant current. Yeah. Do you remember this ideal current source that we always draw? The voltage, the current is always constant, regardless of what is the V across it. Good point. Yeah, this is something very confusing. Right? When you see current source, then you do not fix the voltage across it. You only know that you always access the constant current, no matter what voltage. The voltage is going to solve by the rest of your circuit. Just like the voltage source. When you see a voltage source, you know that this is VCM. But what is the current? You never question about whether this current should be zero or very large, right? The current depends on the rest of the circuit. Yeah. Counterintuitive, but this is something you need to force you to accept it. Always follow this condition. Okay. Good. Very good question, right? Now, then when we are talking about the common mode, we will ask, now it's not treating it as a noise, right? You need to bias it anyway. This slide is like noise, biasing plus noise. Now let's don't think about your noise, we just bias it. We can bias it at 0 volt, 1 volt, 5 volts, whatever, right? What? Can I really bias this at 0 volt in this case? Why? You will turn it off, right? Very good, right? Because with the bias. Can I bias it at VDD or 1000 volt? You say no, why? VG will be too high. What's the problem of VG being too high? I get more current, isn't it? No, there's no current because this is not connected to any places, right? Yeah, there will be current on the branch, and then what happened when the current is too high? What happened? Very good, right? So when both of you are right, when VGS minus VTH, let me just don't say when, right? We need, right? We need VGS minus VTH to be what? Smaller than VD, so that it is in saturation, right? So if your VG is too high, you have very large current, a lot of potential drop, then you are in the linear mode, right? If you don't see it, when VG is high, then ID increase, then Vx, which is equal to Vy, which is equal to VDD minus I. Actually, VD does not increase. I'm sorry, because in this situation, VD, ID does not increase. Because ID is always ISS divided by 2. Okay, you just keep increasing your VG, right? When VG is high, right? VGS is too high, then eventually you go into linear mode. Okay, so let's say again. So what is the situation? We want VG S minus VT. The maximum you can have is when it is equal to VD. Okay, and what is VG in this case? VCM minus Vs, do not miss the Vs. And then here I actually need to be complete. I need to put VDS instead of VD, right? We need to reference to the same page. Minus VTH equals to what is VD? VDD minus ISS divided by 2RD. And then the whole thing minus Vs, right? Because this is VD, right? And VDS is VD minus Vs, right? You need to be very careful with this one, right? Of course, then Vs got canceled. Okay, so based on this, we need VCM to be smaller or equals to VDD minus ISS divided by 2RD plus VTH. Right? I just move VTH to the right. Let me check if this is correct. And that's it, right? The math is not difficult. The most important thing is you understand what we are doing. We understand that when the gate voltage is high, eventually you'll be higher than VDS plus VTH. Once you exceed that level, it will go to the linear region, right? Then the gain will reduce. So you cannot bias your common mode too high. Okay. Okay, if no question, let's move forward. Let's just use what we have learned before. Instead of asking what is the maximum VCM, now how about ask what is the maximum RD I can have? Why do I want to have a large RD? If it is a common source, why do I want to have a large RD? You always only have a few figures of merit, right? The gain, the input impedance, output impedance, GM, frequency response. Why large RD is good for a common source? Not here, we have not learned how to find the gain, but why it is good for a common source? Large RD. Yeah, exactly, right? A lot more gain. And what he tried to say is to really deduce the equation. He said a small change of current will produce a large change of voltage, Ohm's law, right? But finally, that's what you said, larger gain. Yeah, you want to have large gain RD, right? So your boss asks you to design an amplifier, you want to a certain gain, then you just put a very large RD to it. But it cannot be too large. Why? Due to the same reason. If RD is large, then you have a large potential drop, VD will be small, then you go into the linear mode, right? So still you need to follow the same equation. So I'm going to copy the equation here and you can try to see how to do it. I just told you that VCM needs to be smaller than VDD minus ISS divided by 2 times RD plus VTH. So what is the maximum RD I can have in this case? I just use the same equation, right? Can you try to calculate a little bit? Just give you 1 minute. Just think about how to do it. So should not be too difficult. I just rearrange the terms, right? Then I get VCM minus VDD minus VTH has to be, okay, I need to redo it, smaller than, yeah, negative, which is not good. Just need to, so RD needs to be smaller than negative VCM minus VDD minus VTH, right? Divided by ISS divided by 2, right? And you just plug in, my answer is 2.8. Yeah, very good. 2.8 kilo ohm. Now, if you get something ohm, you really need to double check because a regular circuit usually is in the kilo range. Why is that? Because your GM is in the milli Siemens range. And usually the gain is about 1 to 10, right? So they should be in that order, okay? All right, good. This is minor calculation. So now we continue to introduce a few more concepts, okay? The first concept is the equilibrium overdrive. So what is gate overdrive? We talked about gate overdrive before. I wonder if you still remember. The gate overdrive, let me remind you, you have a current, right? Just a regular transistor. ID equal to W on L mu C ox divided by 2 VGS minus VT squared, right? You only have current when VGS minus VT is larger than 0, right? If you draw the ID VG curve. This is VG. This is ID. How would it look like? When you have a small VG, what's the current? 0, right? And then you will pick up only at what point? VTH, right? So you see that it only has effect when you are larger than VTH, right? And that's why we call this the gate overdrive, right? How much you overdrive the threshold voltage determine how much current you have. So this is an important concept, right? It also depends on, it's just like the baseline. You have two transistors, you're competing with another vendor. They said they have a much larger current than yours when they bias at 1 volt. When you bias at 1 volt, yours is only half of theirs. That's not a fair comparison. You need to say, what's your threshold voltage? Maybe I already get this amount of current by having 0.1 volt overdrive. And they might actually have 0.5 volts overdrive, right? So you need to compare what is the overdrive on top of the threshold voltage, right? So that's why VOV is something we care about. This is a quantity sometimes we want to mention. Okay, so because of this, then you have W on L. If you want to rewrite this equation, it is just VOV squared. Now you don't see VGS and VTH. I only want to see the net difference. Is that okay? Okay, so then why is important? This is simple, right? It determines the current, right? And then what does it determine when you have a larger current? What do we care about for a transistor again? Transconductance. Very good. This is the key word you really, if you don't know about anything, just say this, probably is correct, right? So your GM is larger. And GM is going to determine a lot of different circuit performance. Okay? Now, here actually I misused a huge space. So now what I'm showing you is the overdrive of a general transistor. In this circuit, what is the overdrive of the transistor? Then based on the equation, you find that what do I need to know? Yes, VGS and VTH, but now I just want to know what is the overdrive, right? So I should, yes, that's one way. But how about if I don't know VGS and VTH? I only want to use based on this equation. What do I need to know? The current, yeah. So your answer was correct. But what is the current here for the transistor? Now SS over 2, because it is at a common mode, right? This is ID equals to ISS over 2. Everyone okay with this? Yeah. So then the result is the overdrive VOV equals to square root ISS divided by W on L mu C ox. Do I need to over 2? Yeah, very good, right? Because I have 2 at both sides, right? So if I know what my bias current is, I know what the gate overdrive will be. Because VGS, beside G, I need to know VS, the S, right? But I don't know usually, right? So I can rely on this. So now you start seeing that this tail current has a very important role in your circuit. You make ISS large, you have large overdrive, then you have a large GM, right? So I just asked you, how do we increase the VOS, the overdrive? Oh, very good. So, okay, one is increase overdrive, and someone even go to the detail, say, how about let's decrease the width, right? and all this. But actually, I don't want to do that. The reason is because the reason to increase the overdrive is to increase the GM. If I also reduce this one just to get a better overdrive, that is not my final goal. My final goal is actually increase the GM. So here I will just keep VOV. But what you are saying is correct. Now, but, sorry, what I'm doing, not overdrive. I increase ISS, right? I want to increase ISS, right? Then I will increase. What is the problem of increasing ISS then? Can I keep increasing to very, very large? Yes, too much power. Increase power. What else? What will turn on? It won't be higher than VT. That depends. But besides that, what was the problem?
You're going to.
No, okay, it's the same. Okay, so now I understand what I say. Yeah. You are both correct actually. Because you are saying that this is fixed at constant bias. VG is fixed at constant bias, and then you think that this one will go up, but not necessarily. This point does not go up, right? Because this is an ideal current source. I don't need to increase the voltage in order to increase ISS, right? Yeah. So the point is it still have ISS divided by 2 on both sides. But what is the problem of keep increasing ISS divided by 2? What? Say again, your VD is going to increase or decrease? Decrease. So if VD keep decreasing, what happens? You go into linear mode, right? Right, because the VD equals to VDD minus ISS divided by 2. You keep increasing ISS, then you go to linear. On the other hand, just say you make your design more difficult, less headroom. Because you try to change something else, you may go to the linear regime, right? So, but anyway, right, that is what you want to know, right? I mean, in the future, this is maybe some basic knowledge, but in the future when you design a circuit, it's same in other engineering problem. Nothing comes for free. If you get something good, as a good engineer, you always need to think, what am I giving up? Okay, no free lunch in engineering. If there's free lunch, that just means that your circuit is not optimal, right? If you have some very lousy stuff, you can improve everything at the same time. But when you're pretty good, for getting something, a best-selling products from another colleague, then you better be careful, right? Okay, good. So now let's go to differential operation. We are very good about